Welcome to Electronic Seed YouTube channel. Today in this video, we will learn about Boolean algebra, essential laws and rules. Let's get started. Boolean algebra is the foundation of digital logic design. For example, consider a pressure sensor labeled P, temperature T, and a manual override M. Boolean laws help turn messy logic into clean, minimal expressions. We will cover complement, identity, distributive, associative, commutative, priority, and De Morgan's laws. You will learn to simplify complex expressions and reduce the number of logic gates. We work with binary variables 0 and 1 using 3 operations: and, or, and not. Rules govern how variables interact with themselves, their complements, and the constants 0 and 1. The complement rule means a sensor, and its inverted signal can never be active at the same time. Identity law says and with 1 or with 0 passes the signal through unchanged, like leaving unused inputs alone. This table summarizes the identity and null rules for both and or operations, showing how each interacts with constants 0 and 1. Commutative law says a plus b equals b plus a, and a and b equals b and a. Associative law says that when adding 3 variables, grouping the first 2 or the last 2 doesn't matter, and the same holds for a and d. These laws let us reorder and regroup terms without changing the result. For a multi-input AND gate, the order of inputs doesn't matter, which synthesis tools take advantage of. The distributive law is the most important tool for manipulating Boolean expressions. First form, a and b or c, equals a and b or a and c. Second form, a or b and c, equals a or b and a or c. This second form has no equivalent in regular arithmetic. It arises because addition and multiplication here are idempotent and complement each other. To remember or over and, notice the operator inside the parentheses flips from and to or. In a real safety system, the alarm triggers if either temperature high and pressure low, or the door is open. Using the second distributive law, we can factor the expression to use fewer gates. Not the complement operation has the highest precedence. Next comes and finally or has the lowest precedence. For example, in a plus b and c complement, we compute c complement first, then b and c complement, then or with a. Parentheses can override this default order. Ignoring priority leads to mistakes, especially when applying De Morgan's laws. The complement of a ORB equals a complement and B complement. The complement of a and B equals a complement or B complement. In words, the complement of a sum is the product of the complements, and the complement of a product is the sum of the complements. These laws are indispensable for converting between NAND and NOR logic families. Suppose a system requires the complement of X or Y complement. By De Morgan, that equals X complement and the complement of Y complement. The double complement cancels, leaving just Y. The final simplified expression is X complement and Y, a simple AND operation. This is one of the most frequently used simplifications in Boolean algebra. Let's derive it using the second distributive law. We start with a plus a complement B, and rewrite it as the sum A plus a complement, A and D'd with a plus B. By the complement rule, a plus a complement equals 1. Then 1 and a plus B simplifies to just A plus B. The dual form is a complement plus a B equals a complement plus B. This identity eliminates a redundant complement term, removing an inverter and an AND gate. Consider a motor controller with start signal S, thermal fault F, and emergency stop E. The original logic expression is S or S complement and F and E complement. Apply the reduction A plus a complement B equals a plus B, with A as S and B as F and E complement. We get S plus F and E complement simplified. This simplified form removes any dependency on S complement. This result isn't obvious from a truth table alone, but follows directly from Boolean algebra. Our variables are X for motion, Y for door open, and Z for window closed. The original alarm expression is XYZ complement plus X complement YZ complement plus YZ complement. Step 1. Factor out yz complement from the first two terms, giving yz complement times x plus x complement plus yz complement. Step 2. By the complement rule, x plus x complement equals 1, so we get yz complement times 1 plus yz complement. Step 3. Using the idempotent law, yz complement plus yz complement simplifies to just yz complement. So the final simplified expression is simply y and z complement. This simplified form uses only one AND gate for y and z complement. The original expression needed 3 AND gates and an OR gate. This reduction lowers power consumption and reduces propagation delay. We use Boolean algebra to minimize logic gates in FPGA and ASIC designs. It helps convert arbitrary logic into NAND-only or NOR-only implementations. You can verify equivalence between two circuits without exhaustive simulation. It simplifies Boolean equations derived from Carnot maps. For more, check out the external resource all about circuits on Boolean algebra. Automated synthesis tools handle most simplifications today. But debugging timing or optimizing critical paths still needs human insight. These laws remain relevant for quantum logic and reversible computing. Mastering Boolean algebra solves problems that purely algorithmic methods may miss.